Okay, then we go to the lecture. We stopped last times here about the instantaneous center of rotation and to know how to construct this center of rotations means that the center of rotation, it's only the center here where the velocity is equal to 0. Okay, this means the center of rotation. That is means if this body here, if this body is rotating, that it will rotate around this point here. That now how to draw it or how to know where is exactly when you have any body, you know where is the center of rotation. If we know two points on this body where we have their velocity, that it means in our case here, for example, you have the point B, you have the point C. What we need only to know the direction of this velocity. If we know the direction of the velocity, what we have to draw only the line perpendicular to this velocity here. Then you have the here, which is velocity of the point C. Here, we come back, to this RMC. Now, we know the line direction of the velocity here, VC. We have the second velocity, VB, and we know the line direction. What we have to do is only to draw the line, the perpendicular or the normal to this velocity, the line, the second line perpendicular to VB, and the intersection of the two velocity of the two lines will give the point M. And this M, it's only this point here has no velocity. Okay? That it means now the instantaneous center, we call it point M, in a rigid lamina moving in its own plane. Yeah. The velocity at the instantaneous center is 0. That it means the velocity Vm at this point here is equal to 0. All other points move according to the relationship for the circular motion around M. Now, if you want to know any point on this rigid body here, for example here, if we want to know the velocity, then we have only to keep the distance from this point to M, and this distance here will give the velocity of this point. Why? Because we know omega, which is the angular velocity, and angular velocity for the whole body here is the same at any point. Now, if we want to know the VC, it's only the distance RMC multiplied by omega. You remember we said in the formulations to determine the velocity of any point, it's only the vector r cross omega. Then it means we have now, if we do it, for example, graphically, let's say we have to take the distance here from M to C, we measure it, and we multiply it by omega, we will get here the velocity Vc. The same for Vb. We take the distance here, Rmb, and we multiply it by omega, we will get here the velocity Vb. Or this is the scalar. That is means if we do it graphically. Now, if we do it by vectorial product, in this case, what we have here, we have Vb, it's omega cross Rmb. The same here, we see it's omega cross Rmc. Then we have plane equation of motion without frame velocity since Vm is equal to 0. Okay. Now, the methodology is the following. The direction of two velocities are known. It happens that you know the direction only, yeah, but you don't know the values of these velocities, or you know the values. In this case, you have only to take to consider the directions. Sometimes it's given the instantaneous center of the velocity. Okay, when it's given, you know the distance to Vc. Only here you can determine the direction of Vc and Vb. It's only to draw the line, and you make perpendicular to this line, you will get the direction of Vc as well as for Vb. Now, for the instantaneous sense, there is always a pure rotation. That is means pure rotation. It's not sliding. Yeah, it will rotate around this point here. The velocity vectors are perpendicular to the position vector of B and C with respect to M. That is means we have the direction here of Vc, we have the direction of Vb, we draw the two lines, okay, we will get the center of rotation. Then the instantaneous center is the intersection of a point of this perpendicular line here. Direction of rotation is still undetermined. Now, if from the direction of Vb here, it follows the direction of rotation and the direction of Vc. From the magnitude and direction of Vb, it follows the direction of rotation, the angular velocity and the magnitude and direction of Vc. That is means here now, we know the direction, we know the magnitude of Vb, okay? Now, if we have this, we can determine the direction of omega. From the magnitude and direction of omega, it follows the magnitude and direction of Vc, Vb, and Vc. Now, this is to determine if we have the direction of two velocity, or we know here we have three unknown, let's say. Either we have the direction of one velocity, we have to determine the direction of the second velocity, and we have to determine also the direction of VB, of the center of rotation. For the instantaneous center, there is always a pure rotation. The velocity vector are perpendicular to the position vector of A and B with respect to M here. As M doesn't move, that it means doesn't translate or slide, one gets here R and B, the distance here, R and B, only that we have VB, we make the perpendicular here. Then from the direction of VB and omega, it follows if M is on the left or on the right side of VB. Because it's important here, we can make the perpendicular here, line, but we don't know if M is on the left side or M will be on this right side here. The direction of omega will determine if it's on the left side or the right side. If we have omega in this direction here, rotate like this, in this case, we keep M here on the right side. Now, for example, we take slider crank mechanism. Yeah. In this case, what we have here, we have the mechanism, the pistons, it's translating on this direction. There is only the keep it here, lock it on this direction, vertical direction. There is only horizontal translation. You have here, this point is rotating with omega 1. Okay. Now the mechanism, you have the rotation of this, let's say, bar or arm here. It's rotating with omega 1, but at this for the second one here, it's rotating with another velocity. It's not the same as this one. Why? Because the point B here, the connection, it's not fixed. Okay? I hope I can get here the video that you can see it. You see it here. We have this point here, A, it's fixed. It's rotating with certain velocity, the red one here, the, let's say, the bar or the arm, it's rotating here, the red one, with certain velocity, omega 1, okay? And you have the blue one here, it's rotating with another velocity, okay? What we have here, we have here the piston, it's only sliding along this direction, the horizontal one, okay? Now the question, why is the position of this instantaneous center of rotation? Okay, that it means here, if we take this point here, this is rotating, let's say, with omega 1, not this one, but the arm here, from this point, fixed point here, to A, it's rotating with omega 1, this one, the red one. Yes? It's everything is okay? because I heard the voice. Okay, if not, I will continue. Yeah, I can continue.
Yes, sir, you may continue.
Okay. Then we have, as we said, that here, this part here, from this point here to A, this is the red one,
Are not
is
sharing
rotating with omega 1, and the second one here has not the same the same,
Sir,
yes,
we cannot see your screen.
okay, one moment. Okay, then I said that is the part, the left part here, it's rotating with omega 1, and this part here, it's rotating with other velocity. Let's say call it omega 2 or. Now we have this piston here, it's sliding only horizontally. That means it's moved only in this direction. Okay. Now coming back to get the instantaneous center of rotation. Then we have here omega 1, the point A. We have the point B. We have the arm distance here, RAB. Yeah. What we know only VB. Yeah. Can be determined as VB. It's only V of this point here, A. This is what we know from the equations, plus RAB cross omega 1. Okay, this is the equation what we get if we have 2 points. To get the velocity of the second point, it's only to use the velocity of the first point, yeah, and we have the distance between the 2 points cross the angular velocity. What we know, this is the point here, it's fixed. That means the velocity VH equal to 0. Then we get, yeah, velocity of the point B, it's only VB. Sorry, it's B, it's only RAB multiplied by omega 1. Now, if we know the distance, yeah, we know the angle of rotation, we can determine the magnitude of VB. As it's only cross product of 2 vectors, yeah, that it means now omega 1 is rotating, yeah, in the direction of the plane here, perpendicular to the plane. This is the direction of omega 1. Yeah. Here it's outward. Yeah. Then it means now the vector omega 1, it's the direction of omega 1. Now we have RAB, then the perpendicular to the 2 vectors will give the direction of VB. Okay, and VB is only perpendicular to the vector position here, RAB. As well, it's perpendicular to omega 1. Now we have the direction of VB. Okay, and if we know omega 1, then we can get the magnitude of VB. Okay, if we don't know the omega 1, the magnitude or the value of omega 1, in this case, we don't know the magnitude of VB, Yeah, why? Because VB is only omega 1, RAB multiplied by omega 1. Okay? Now, what we know the direction of VB. Yeah, we make the line perpendicular to this velocity VB. Okay? Second, now, we know the direction of the point C, the piston is only horizontally, moving horizontally. In this case, also we make the line perpendicular to it. Yeah. Now the intersection here of these two lines will give the point M, which we call it instantaneous center of rotation. Means that the point here, the M at this position here is equal to 0. Okay? Now coming back, we don't know the velocity, for example, of VC, yeah, but we know, we don't know the magnitude of VC, but we know the direction, okay? We know the velocity here is 0, okay? Now what we have to do, the velocity of the point P can be determined either by RAB omega 1, that it means here we have omega 1, we have this distance here, then we can determine VB. If we don't know omega 1, what we have this distance here from B to M, we measure it or we determine it, okay? And here we get the second relation, RMB, it's only multiplied, VB is only RMB multiplied by omega 2. There is the equality here now. Now, if we read off reading of the distance BM or MB, we read this distance here between the 2 points. In this case, we can get the angular velocity omega 2. Okay, we said the velocity here is 0, but it's rotates, the whole system here is rotating on this point here. And then we can get omega 2. Okay, now if we get omega 2, yeah, then the direction of BB rotation on the sliding crank counterclockwise. The piston speed now, we can determine it by VC. It's only RMC multiplied by omega 2. Then it means now, we know omega 1, we know the distance AB, we determine now VB, okay, the velocity, magnitude, as well as the direction. From this now VB, we have the second relation where we determine the position M. In this case, we can get the second relation RMB multiplied by omega 2. Then we can get here, we know RMB, this distance here. Then we can get omega 2 now. Okay, getting omega 2. Okay, now we know the direction of VC. We know the distance between the 2 points M and C. In this case, by calculating omega 2, we come here and we get the velocity VC. Okay, this is the principle. Yeah, and we will see it, an example in tutorial. Now the case of, for example, here, rolling wheel, yeah, it's this wheel, yeah, it's rotating, okay? For example, when you see here omega, it's clockwise. In this case, that it's rotating in this direction here. Then we have always the contact point M with the ground, okay? Now, if we do this, that at the center M, the support point, if no sliding occur, okay, it's very important. There is only the rotation, but there is no sliding. That is means this point here, okay, let's say this wheel not translate like this, okay, it's only rotate. That it means now the contact point here between the ground and the wheel, this point is always the velocity is equal to 0. And it will be, yeah, for the point where the velocity is equal to 0, it's the instantaneous center of rotation. Then we have linear distribution, yeah, over the height of the wheel. In this case, we have here the diameter of the wheel. Now, the velocity of the center of mass here, the S, okay, we make only this direction. Why? Because we can take 2 points B and M, yeah, we draw the line, and after this perpendicular to this line, as the two lines coincide here between the point, for the point B and the point S, we make the perpendicular to it, then in this case, what we have the direction of B and we have the direction of the center of mass. Then the velocity here, the S, at this point here, it's only R, the radius, multiplied by the angular velocity. The VB will be the distance RMB multiplied by omega also. Then it's only 2 times R omega. Why? It's here the diameter here. Okay. Local displacements change. Then we have the S. It's only RdV. Integration with S for phi equal to 0 at the rest here. For phi equal to 0, the distance is equal to 0. Then in this case, we have R phi. Yeah, we make the here the angle phi here. Then we have the sinus or the tangent. It's a very small angle. There is no distinction between the tangent phi and the angle phi. That is means tangent phi is only phi, or sine phi it's only phi. Then we have here as this distance here, not the velocity. That is means this distance from this point to this point here will be a radius here multiplied by the angle here phi. Now we have here the center of rotation will be only on the ground. That is mean we have the initial position here and we have the actual position here, yeah, described by the dashed line. Now what we have here, for example, if we return back, if we want to calculate the velocity of any point on the wheel here, if we take, for example, the point C, we want to know what is its velocity. It's only to draw here the line from the instantaneous center M to the point C. Okay, we draw the line here and we make the perpendicular to it, the line perpendicular to it. When we get the line perpendicular to it, we know the direction now of the velocity Vc. Okay, when we know the direction of Vc, we get the distance, we measure the distance between M and C, okay? And if we want to get the velocity of Vc, will be only the distance RMC multiplied by omega. And then we get the magnitude of the point C. As I said here, M0 and M1. Now, the initial position, M0, and the actual position, M1. M0 and M1 are the instantaneous center of rotation. Now, if we want to determine here the distance of the wheel, circumference is only here R phi if no sliding occur. Okay, there is only a rotation. If there is sliding, the value here, this distance M0 and M1, will change. That it means there is sliding. We take this part of the sliding and plus the cover distance due to the angular velocity here, omega, or we call it also phi dot. Now we take here this example, we will see it in tutorial, okay? Now what we have here, we have the sliding ladder, the top end A here moving down, okay, the wall, and the bottom and B here across the floor away from the wall. That is means this point here moving down, and you have B, it's moving in this direction. Okay. Now, as it's this point moving down, that it means its velocity, it's in this direction here, vertically. The point B, moving horizontally, that it means we have the velocity in this direction. Now we know the direction, the line direction of A, the velocity VA, and the velocity VB. We have only to make the perpendicular to the both, okay? The intersection now, we give the instantaneous center of rotation M. Getting M, okay? Now what we have, we can measure RMA and we measure RMB, okay? The system or the ladder will rotate with certain velocity omega, Then in this case, we have here, that is means here when it's down, here getting down, and here horizontally, that it means each point here, it's rotating, okay? And it will be only here in our case, the phi dot, okay? Omega will be the phi dot, not the angle phi, but the velocity, the angular velocity phi dot. Then we have VA, we can determine it. Now we know the omega, we measure the distance R and A, and we get VA. The same principle for the point B. We measure the distance R and B, we multiply by omega, then we get here the, let's say, the velocity VB. The angular velocity V omega is only taken here from this relation, V R divided by R and A. It's only VE L sinus phi. RMA, okay, we have it here, VA divided by L, RMA is only L sin phi, and RMB will be only L cosine phi. Then we have here the relationship between the velocity VA and VB, okay. If we know the magnitude of VA, we can determine it by VB as we know that the angle phi here, or if we know VB, we can get VA, okay. Now we look here, for example, that there is what we call the fixed centroid. That is means here now what it's describing the ladder. It's describing only the quarter of the circle. Means we have the initial position, for example, here, okay. Then we have, for example, A5. It's moving, the point A is moving to this position at time T4, okay? And after this, moving to T3, T2, and T1. At T1 will be, yeah, the laser will be at this position here. The same principle here. We have A5, okay? Then we have here B5. For A4, we have B4, and so on. Now, at each position, we draw the center of rotation. In our case, at time T5, the center of rotation as the point B is at this position, the point A at this position, okay? Then we have N5 is here. Now, at time T4, in this case, what we have the direction of VA, we draw the perpendicular, the direction of VB at time T4, it's in this direction, we draw the line, and we get the center of rotation. The same principle will be used at T3 and T2. What we see the intersection now, if we join here the line of at each time here, we see it's only the quarter of the circle. And this will be called the fixed centroid. Okay? Then the fixed centroid is only equal the locus of the instantaneous center, we call it EC, in the fixed plane. Example here, sliding ladder. This is the previous example. Now the construction of M for 5 different positions. In this case, as we have here, fixed centroid is only an arc or quarter of the circle. As you see here, that it means now we have the system here, fixed coordinate system, which doesn't move, it's absolute coordinate system, and we have what we call the relative coordinate system. That it means now the relative coordinate system time y prime, it's changing as you see it here. That it means it will rotate, relative to this point here. And now if we take the 2 points, for example, A2, A4, we have M4 for this point. This is the center of rotation, and we have M2 for the center of rotation of this one. Then introducing what we call the fixed coordinate x prime and y prime, but this one, the fixed coordinate system, it's rotating relative to this fixed coordinate system. This point is fixed, then we take it as this is, we will see it, during the next lectures, to make a distinction between fixed coordinate system and the relative coordinate system. Then we have here moving centroid. It's sequence of instantaneous centers in the body fixed coordinate. Okay, and here there is only semicircle with R, which is the half ladder length. Now, for a plane motion, the moving centroid is rolling on the fixed centroid. Means if you are here at this position, someone, for example, is sitting here at this fixed coordinate system, the global fixed coordinate system or absolute coordinate system, okay, what he will see that the center of rotation is describing this arc here. But if someone is sitting here on the local coordinate system, fixed local coordinate system, we see that it's describing this circle. That it means now this arc here will touch at each time this, um, let's say here, moving center out here. Now we saw that there is the instantaneous center of rotation, and there is also instantaneous center of acceleration. Okay, the same principle, nearly the same, yeah. The instantaneous center of acceleration is one point where the acceleration is equal to 0. Okay, that it means any point where the acceleration is equal to 0. In this case, we call it the instantaneous center of acceleration. It's nearly the same. The difference is the following. If we have, for example, now the acceleration, let's say, of the point C, it's AC, okay, and we have the acceleration of the point B, it's AB. Now, what we have the difference between the instantaneous center of rotation and this one, the instantaneous center of acceleration. For the instantaneous center of rotation, we make only the perpendicular line to the velocity, and when we get the intersection, the intersection point, in this case, we say this is the center of rotation. Here, the difference is that we make an angle beta, okay, withdraw from the line direction of the acceleration of the point AC, we make angle beta. The same principle here for the acceleration on AB of the point B, we make an angle here beta, and when we make the angle beta, withdraw the line, angle beta withdraw the line, and the intersection of two lines will give the point F where the acceleration is equal to 0. This is the difference. Okay? The difference is only to make here, for this case, for the center of acceleration, we make only the angle beta. Yeah. For the rotation, there is no angle beta, which means it's 0. Okay? Now, instantaneous center of acceleration F, velocity and angular velocity are known. Yeah. When we know the velocity and the angular velocity, the acceleration of point B can be described, yeah, by the following relation. We have seen it, yeah, in the previous lecture. There is the acceleration of any point here at, okay, plus 2 acceleration, the tangential one and the normal one. Okay. In this case, we have AF as it's the instantaneous center of acceleration. The value is equal to 0. Okay. Then it means AB can be determined now by only the tangential part and the normal part. The same principle, we use it for the point AC. Okay. For AC is the same. ACF tangential plus ACF normal. Now, if we looked at to ABT, we know from the previous example lecture that we have here the tangential one, yeah, and this is only RFB, the distance FB, the position here RFB, multiplied by phi dot square. You remember the equation? It was R FB cross omega cross omega. Okay. For the here the tangential one now we have here it's only R FB phi dot dot. That by expression vectorial it's only R FB cross omega dot. Okay. The same principle here for the point C. The equation will not change. Okay. It's always for the normal, it's R omega cross omega. And for the tangential one, it's R omega dot. Then we have here B phi t. The acceleration in tangential direction is R FB phi dot dot along the direction AF, the normal one. If phi, which is the vector here, phi, and we have here an. Now, for the normal one, it's only here R FB phi dot square an. Now, at each point of the body, there is the same angle beta between the position of vector and the angular velocity. And here we turn always counterclockwise with phi. Okay. Then we have tangent beta. If we look now here, tangent beta, if we take it, it's only this part, which is the vector here, ACFT, divided by ACF and then we have RFB phi dot dot divided by RFB phi dot square. We have the same position in RFB, that is mean will be defined always by phi dot dot phi dot square. If we write it in angular velocity or angular acceleration, will be here omega dot divided by omega square. The same principle if we take the position, the point C. Okay, we will get the same equation. Then for given angular velocity and angular acceleration, we can determine the angle beta here. Now, the rule to determine the instantaneous center of acceleration, F, case 1, there is for the given two acceleration vector of point B and C, draw the angle beta. The intersection point gives the instantaneous center of acceleration. That it means now, knowing the vector here AC, it's only the sum of the two vectors, the tangential one and the normal one. Okay. Now what we do here, we draw the angle beta, we make the intersection, okay, and we get the instantaneous center of acceleration. Now, rule to determine the center of acceleration here, case 2. Draw the angle beta for the acceleration vector of point C. Okay, we know only the value of AC. What we do here, we make the angle beta and we draw the line. We get the point B. Now there is three possibilities to calculate RFC. Okay, either we take here AC, the acceleration, sine beta, that is mean this position here. It's only the normal one, RFC phi dot dot. Then we get RFC from this relation here. Of course, knowing here the acceleration AC, we know phi dot dot, and we know the angle beta. Now there is the second relation, which is here the tangential one, AC cosine beta, it's RFC phi dot square. Then we get here RFC, okay, from this relation as function of phi dot square, and here as function of phi dot dot. Now the acceleration, the magnitude of the acceleration, it's only, yeah, here the sum of the normal one square plus the tangential one. Then we put away RFC, then we can get here now the RFC, the value of RFC, knowing AC, the acceleration of the point C, and we know the angular velocity and the angular acceleration. The case, for example, of the rolling wheel, yeah, we have here, we know the angular velocity, we know the angular acceleration, and we know the velocity of the center of mass, AS, the acceleration of the center of mass, AS, and we know its velocity, VS. Now, the velocity of the center of gravity, here, VS, or the center of mass, is only R phi dot. The acceleration of the center of mass here, AS, is only R phi dot dot. Now, the acceleration of the instantaneous center of rotation, AM, yeah, it's only AS plus, in this case here, then AS at this position plus the non-tangential one plus the normal one, okay? This is what is component of the acceleration of the instantaneous center of rotation. What we have here, we have AS, it's known. We have AM, it's known, okay? And we have here the tangential one, okay? Then when we make here, we get this value, it's equivalently to R phi dot square. Now the acceleration of the instantaneous center of rotation is directed to the gravity center, okay, to the center of mass. The construction of the instantaneous center of acceleration is only the rho beta, angle beta in S and M. Then what we have AS, we know the direction, we know its magnitude, we have AM, the center of rotation, its acceleration now, yeah, and now the value we know AS, okay, here in this case we know the value, then the magnitude, which has two components, yeah, we have the component which is the normal one, and we have the component which is the tangential one. Now, if we have here normal one, then what we make an angle beta, we draw the line, the same for AM, getting it back here. Then in this case here, we draw also, yeah, clockwise, the angle beta, then the intersection of the two lines will give the instantaneous center of acceleration. And as you can see, the point M is different from the point F. The instantaneous center of rotation where the velocity is equal to 0 at this position. But the position of the instantaneous center of acceleration is at this position. That is means at m v is equal to 0, yeah, but there is acceleration. In this case here, the acceleration f at f, the acceleration is equal to 0, but there is velocity. Okay, I um, stopped now with the the second part of the slides. Yeah, coming now to the third part, and the first part and the second part are only how to determine the acceleration as well as the velocity. That is means is only a matter of kinematics of the bodies. When we determine this, okay, the aim, of course, is to describe not only the kinematic, it's also the kinetic of this um, any particle or any body. Now we will use these equations now coming to the third part where we have to determine the forces, yeah, or the moment of, I think you have seen this, how they determine for static, not moving bodies or structure or mechanical system, yeah, we get this only for static. That is means we neglected always. We neglect. It's not visible because I have finished with the part 2 and I will come to the part 3. Okay, I'm explaining now why we use this part 2, part 1. Okay, and I pointed out that I divided the lecture to, let's say, several parts to make distinction between each part. Okay. Now, if coming from this case, uh, in mechanics 1 as well in mechanics 2, yeah, you have seen only bodies or mechanical system not moving. That is means there is no dynamic effect. It's only static. Static means doesn't move. So you look each point on this body, yeah, this determine the forces and so on, but the acceleration and the velocity were equal to 0. Now in mechanics 3, we have to consider this acceleration and velocity to determine the forces and so on to get this forces and also the moment. Okay, now I switch now to the slide. Be patient one moment. Okay, now, as I said, we have to determine now in this part, and this part is only the kinetics of rigid bodies. Yeah. Now, previously, the determination of motion with the help of the kinetic variable. Yeah. Position, velocity, and acceleration. Now, the cause of motion or change of motion is not considered. That it means now, in mechanics 1, in mechanics 2, we had only static case. That it means the motion has, or the change of this motion have never been considered, yeah, in the equations. We never considered the acceleration. You have done always the sum of the forces, the equilibrium equation, the sum of the forces, yeah, is equal to zero. Okay? But in any case, zero, it means if it's equal to zero, that is the equilibrium, but you never consider this zero. It's really if the body or the car or any mechanical system really moves. If it moves, that it means it's not zero. This is what we will see. Okay? Based on what we have seen from the kinematic part, position, velocity, and acceleration. Knowing this, we can get now the forces and also the moment. Now what we have seen that, not really seen, but we describe it. There is Galileo Galilei, yeah, on the CS here, definition of velocity and acceleration. This is what he has done, yeah. But force as a cause of change of motion, it's not clearly defined. Then no formulation of the law of inertia. Inertia, that's what we call the inertia, that is mean there is motion inside. Yeah. There is also Johannes Kepler, okay, the laws of planetary motion, okay. The orbit of the planet are ellipses with the sun at one focus of the ellipse. The line joins the planet to the sun sweep out equal area in equal time as the planet travels around the ellipse. It was, but the important thing, it was also considered only kinematic variable, but not the kinetic one. Okay? And comes what we call Isaac Newton. You know this history with Apple. Okay? There was first clear definition of the concept of force. Okay? Then federation of Galileo finding with that of Kepler, the reason that a stone fails and the planet remains in its orbit, yeah, in both cases, the gravity force is the cause of the change of the motion, yeah. And there is here for Newton law, three Newton's laws, yeah, principia, justification of the kinetic. There is the kinetic, the motion, acceleration, velocity, and so on, yeah, but there is no explanation behind this, okay? But Newton came and explained this by what we call the three laws. Okay, there is the first law, the second law, and the third one. Now, before to come to this, I put the video explanation, but Galileo Galilei, okay, that we consider always is there is no let's say, in the motion, yeah, there is no air resistance in the equations. Okay, I put one video about the principle of Galileo Galilei, that it means if there is no air resistance, yeah, the weight of the body do not play a role. Yeah, that it means if you put fell down, let's fell down 1 gram, okay, and 1 ton, if there is no resistance of the air, that it means they will come to the ground at the same time. Okay, I put this in Moodle. I let you, let's say, 4 or 5 minutes to see this video. Yeah, only one moment. Okay, I turn back. As you have seen, that it means that if there is no air resistance, in this case the weight, yeah, doesn't do not play a role. Okay, and in this case that all body heavy or 1 gram with 1 ton, yeah, will have the same, yeah, let's say, velocity. Now coming this extraction to this, then we have what we call the Newton laws. There is the first Newton law. If no force acts in a particle of mass m, the momentum remains constant. That it means now if we define the momentum, we note it by b vector at time t. It's only the mass at time t multiplied by the velocity at time t, and it keeps always constant. Yeah, that it means the momentum at time t0 is the same at time t1, and it will be the same at time t2, and so on. Every object remains in a state of rest or uniform motion of constant velocity unless an external unbalanced force acts upon it. Like for example, for let's say the gravity, yeah, will act on it. If it will act on it, then in this case that there will be the change. There is the second Newton law. The second Newton law, if a constant force acts on a particle, yeah, for a given time, t, the product of a force and the time interval, what we call the impulse, is equal to the change in the momentum. That it means here, if we have the force F, now the change of the momentum B here with respect to time, that is only d by its definition as the mass multiplied by the velocity. Yeah, this is will give the force. For a constant mass, yeah, there is no change here. For example, m do not depend on time, like for example in the orbit, yeah, you have Apollo going, that's losing, yeah, fuel and so on. It's clear that it will change the mass will change with the time, or losing, yeah, or you keep something like you have car, yeah, starting with inside it's one persons and coming with the time second persons. It's clear the mass will change, and if it's change, yeah, then in this case there is the momentum and the forces will also change. But for a constant mass, okay, m do not depend on time, then in this case we keep it out of the derivation equation here, then we will get dv over dt. But it means the forces now, it's only the mass multiplied by the time derivation of the velocity. And we have seen that it's only v dot, it's only the acceleration. Then we have the force, which is equal to the mass multiplied by the acceleration. This is the second Newton law. Now, we imagine that we have the free fall. This is what we have, for example, so on the video, there is only gravity force G is applied. Okay, that is means there is air resistance. The acceleration near the Earth is known as 9.81 meter per second square. Then it means we can say now the gravity force G is only the mass multiplied by the gravity acceleration or gravitational acceleration gravitational. In this case, that we can get the mass, it's only the gravity force divided by the gravitational acceleration. Unit, it's only Newton, yeah, referred to the inventor of this second equation. 1 Newton is 1 kilogram multiplied by meter divided by the square, second square. There is the third Newton law. The third Newton law, the force of action and reaction between two objects, yeah, are equal, opposite and collinear. This is, you have seen it, yeah, in mechanics. One, yeah, there is always action and then there is the reaction. Like you have external forces and you want to determine in your mechanical system the forces inside the mechanical system. This is will be the reaction, okay? And the reaction, of course, there is R equal to the action, yeah? Then it means the action will be equal to the reaction. They will have the same magnitude, only the direction are opposite, okay? Now, the second Newton law and the third Kepler law, this is what we call gravitational law, yeah? And we have here the forces, it's the mass of the Earth multiplied by the distance, yeah, divided by divided by the distance square multiplied by the mass between the second and the first uh, gravity planet. Then if we make here free motion, we get two problems. The motion is known and the forces are solved. The forces are predetermined and the motion is solved. This is the two cases can be happen. Now, if we take example of accelerated circular motion, we have circumferential acceleration. As we said, it's only the position cross omega dot omega dot. This is what we call the normal one. And you have the radial one, okay? It's only the position multiplied by omega square. Now, if you want to get the forces in the radial as well as the circumferential direction, in this case, yeah, we have circumferential force. It's only the mass multiplied by the acceleration in the circumferential direction. And we have the radial force. It's only the mass multiplied by the radial multiplied by the radial acceleration. Okay, then it means the radial one we replace it by its value here will be negative, and the forces here we multiplied by its value r phi dot dot, and we get here the forces in circumferential direction. Now the forces are predetermined, and the motion is solved. The acceleration comes from what we have seen in part one. Okay, you look to the slides, what we underlined in yellow color and the frame, yeah, integrative twice the velocity and position, yeah, or the position or the distance. Now we take the example of the free fall. Then there is the vertical throw. Okay, we have gravitational force. It's only the mass multiplied by the gravitational acceleration. We have at time t equals 0, the particle is at this position, yeah, and we come here with the mass falling down, okay, come with certain forces here, yeah. We give at the initial position, let's say, the velocity v0, okay. We take the coordinate system here. There is only one-dimensional or unidirectional motion. In this case, that's here the vertical throw, okay. It's time t equals to 0. We have the velocity v equal v0, and then we have at the position here t equals capital letter T. Then in this case, it's reached certain times, yeah, when there is the vertical throw. At certain times, it will reach, the particle will reach the velocity equal to 0, yeah, and then return back. Now if we take here now the coordinate system, yeah, here it's opposite to the motion, yeah, but here for the vertical throw, the coordinate system x, yeah, it's in the same direction as the motion. The variable of the motion are positive if they are parallel to the axis. Now, if we take the forces in x direction, yeah, if we have one forces, the reaction, let's say, it's only minus mg, okay? The second law now, this is what we have here the second law as it's changing, okay, with the time, yeah, the x position. Then we have fx is only m x dot dot. This is the acceleration. Okay, here we have gravitational acceleration, and here the acceleration at each position or at any time. Then we have the forces Fx, it's only minus mg, yeah, and this is the, let's say, the action, and there is here the second, from the second law, what we call the reaction. In this case, that we get the acceleration, it's only minus g for this case here. It's the same principle here. Okay, we have the same relationship. Then we get here that mg, okay, it's opposite to x. Now, if we have, for example, horizontal and vertical motion, in this case, that's describing an arc. That's what we get here. We have horizontal motion in x direction, of course, and there is also, yeah, motion in vertical direction y. Okay, it's two-dimensional problem, yeah, and we have seen, yeah, in the first tutorial that for the case of ladder, let's say, ladder, in this case, what we had was the stone, that in this case, we decompose the system in x direction and in y direction, and we use the same equations. Okay, let's say the same methodology. Here, what we have the forces Fx, then it's equal to 0. Why? Because there is no forces. There is the gravitational acceleration, yeah, it's given in vertical direction, in y direction. But in horizontal, there is no initial force, okay? And there is no, let's say, initial velocity or, initial acceleration. In this case, the forces is equal to 0. But in y direction here, y, there is the forces, capital letter G, yeah, and the forces Fy, it's always in the direction of y, in positive direction, it's only minus mg. Then we have here, in this case, m multiplies the acceleration in y direction. Then we get here, in x, the acceleration is equal to 0. That means the velocity is constant in x direction, but in y direction, it's only the gravitational acceleration with opposite sign. Now what we do, as we have done it in the first, if I remember, first or third exercise in set 1, we divide like table, yeah. We take the equation in x direction and we take the equation in y direction. We start from the acceleration, yeah. Then to get the velocity, we integrate, we get the constant c1. We integrate the second time, we get the constant integration c2. The same principle will be applied in y direction. Okay. Now, we have the initial condition, of course, to determine the constant of integration. We have x at time equal to 0. It's equal to 0, yeah. Then we get C2 is equal to 0. The same for y direction. We have at time t equal to 0. It's equal to 0. Then we get the fourth constant equal to 0. Now coming to the velocity. The velocity at time t equal to 0, it's, yeah, the particle is thrown with the certain velocity v0, then we get c1, it's only v0. In y direction, it was at rest, yeah, then it's the velocity is equal to 0, then we get c3 is equal to 0. Then what we have here, the equation of motion, that it means the kinematic x for the position, it's only v0, the initial velocity multiplied by the time, and in y direction, yeah, it's minus the half of the gravitational acceleration t squared. Now, we take the guided motion, that is means we have the motion which is guided. Then in this case, a particle cannot move freely, but it's forced to move along a given curve or surface. That this is what we call it guided motion. Then it means active applied force, and this is what we call the weight or the external forces. Okay. In addition, there is the reaction forces, transportations, yeah, frame forces affect the motion of the particle and vice versa. In the application of the Newton's second law, the kinetic reactive forces need to be included. This is the principle. Yeah. In mechanics 1 was not the case. Yeah. We said always the sum of the forces, yeah, are equal to 0. Now we take the particle along circular motion. That means at time t equal to 0, we have the particle with a mass m, yeah, moving along circular motion. Okay. We take this polar coordinate system, yeah, instead to use the Cartesian coordinate system. That means at time t equal to 0, it's at this position, it's move with an angle phi. There is the radial direction, and there is the circumferential direction, represented here by the basis vector or the unit vector. We have the radius r here. Then, if we look now to the weight of this particle, we have here the weight is only g, yeah, mass multiplied by the gravitational acceleration. But there is now the reaction of the ground, yeah, we call it n, okay? If we make the sum of the forces here, we get here now, we have g, we can decompose it into two parts, this vector here, g, in circumferential direction, phi, and in radial direction. In radial direction, we have g sine phi. In circumferential direction, we have g cosine phi. Okay. Now, the particle is released at time t equal to 0 and phi equal to 0. Yeah, from the state of rest. Frictional motion, yeah, on a circular path, then reactive forces perpendicular to the path. Okay, at each position you have n here. If it's come to this position, you have n in this direction. Then there is active forces G, yeah, let's say external force, and you have here now a reactive force N, which reacts to this force to get the equilibrium of this particle. As we said, there is the acceleration, yeah, or here the acceleration. We get here, yeah, r phi dot square as always, yeah, r cross omega cross omega. This is what we get in radial direction, and we have r omega dot. This is the circumferential acceleration. Then we have here the acceleration in radial direction, and AT or EV, yeah, in here circumferential direction. When we get the acceleration, then we can come to the second Newton laws, yeah, in tangential or circumferential and radial direction. Then if we make the equilibrium, we make here the forces minus n plus g sine phi, written back. Then here we have the direction ER, it's positive. Then n is opposite to the positive direction of the axis, radial axis. And we have the second component of the active force. Here is G sine phi. In static, we say the equilibrium will be only n, yeah, minus n plus G sine phi equal to 0. Okay? If there is motion, in this case, we have to add, yeah, the mass multiplied by the acceleration. The acceleration is given here in radial direction. This is, you see, in we gave this equation in the previous lecture. You can look them to them in the slide. And we have here the same principle in tangential or circumferential direction. There is no force reactive force. Yeah, there is only active force, and in this case is G cosine phi. And we have here mass multiplied by the acceleration, the tangential or the circumferential acceleration. Then we have here the two equilibrium, yeah, equations. We have, of course, phi dot dot, or let's say omega dot, yeah, is depend on phi, because the angle phi is changing. Yeah, if we calculate at this position here, for example, we will get another angle phi. If we get another angle phi, yeah, of course we will get also phi dot will change, and phi dot dot also will change. There is what we call the chain rule, yeah, as phi dot dot, yeah, depend on phi, and phi itself depend on the time t. Then we know by definition phi dot dot, it's only d phi dot divided by dt. But phi dot is depend on the angle phi. In this case that we make the chain rule, d phi dot divided by d phi, multiplied by d phi divided by dt. Yeah. Then in this case, what we have d phi over dt, it's only phi dot. Then we have d phi dot multiplied by d phi dot divided by d phi. Now, coming to this, what we get here, if we replace now phi dot dot here, okay, we will get the mass multiplied by the radius, the angular velocity, and multiplied by the derivation with respect to the angle phi of the angular velocity, and equal to G cosine phi here. Then what we do is we separate the variable, okay? In one side only phi dot, and on the right hand side only phi. Then we have mass multiplied by the radius phi dot d phi dot equal to the acceleration, to the gravitational force cosine phi d phi, and here we have only to integrate. What we get, the following equation with the constant of integration c. with respect to now here, phi dot, we can get it from this equation. And of course, to get the constant of integration, we take the initial condition. Phi dot for phi equal to 0 is equal to 0. Then we get c is equal to 0. And now we get here phi dot square is only 2 gravitational acceleration divided by the radius multiplied by sine phi. Now the velocity magnitude, the speed, is only the radius multiplied by phi dot. Okay, r phi dot. This is what we know in our case. R, the position, is only the radius. Yeah. And if we replace phi dot now by its value, we get this magnitude. The maximal for phi equals to 90 degrees. That means if we come now at this position here, yeah, by 90 degrees, okay, what we get the same expression as for, yeah, remember that here only it's like the same expression as the failing particle or failing mass. Then here the same speed as for the free fall with the high r. Okay. Now there is, if we look to the transportation force, that means here, take this force in red color, the reactive force N, or transportation force. Now, if we have here phi dot square, return back, we have take this equation here, yeah, the first equation. Phi dot square has been determined, yeah, from this equation here. Now, only to substitute, yeah, the phi dot square by the value here in the first equation, yeah. Then we get here now, and the reactive force is only 3 times the gravitational force multiplied by sine phi. This is what we get from this example or this simple case. The maximal here force for phi equals to 90 degrees. That it means at this position here, when the mass m come at this position at phi equals to 90 degrees, we have n reaching the maximum is equal to 3 times the gravitational force. The gravitational force is only the mass multiplied by g, the gravitational acceleration. Now what you can see in static n, if we calculate it, there is no acceleration and so on, n will be only g, the gravitational force. Yeah, it's only the gravitational force, but here is 3 times the gravitational force. Yeah, this is now, you see as example, the difference between the static case and the dynamic one. Now we take here the motion with the resistance force. Yeah, a resistance force are always against the motion. Yeah, like you have the brake. Okay, the brake, that it means to try the resistance force try to stop this motion. Yeah, then this is what we call here, they try to prevent the motion. There is the active, which is the applied forces generated by the motion itself, a resistance, friction, and so on, must be included in the application of Newton's second law. There is what we call the column friction, or, yeah, this is here, it's sliding down, okay, the particle, let's say. What we have the reaction of the ground, yeah, and we have the gravitational acceleration is always, yeah, vertical. We take the coordinate system x, y, okay, but there is extra one forces, the resistance. If there is friction between the particle and the ground, in this case, there is forces here against the direction of the motion, yeah, trying to stop this particle. This is, we define it by the friction mu multiplied by the reaction force N, okay? Then the friction force R often opposes the motion, the direction of the velocity. Then it means it's falling down. The velocity is in this direction. If the velocity is in this direction, then you have the forces, or the friction force is always opposite. Now is proportional to the normal component N of the reaction of the surface. Here, in our case, we have, for example, the ground. Factor of proportionality is only mu. Here, mu is only coefficient of friction. And this is coefficient of friction is depend on the material, yeah, like steel, aluminum, and so on, yeah, glass. There is always here, yeah, for each material has its own coefficient of friction. Now, if we take the second Newton law in x and y direction, if we make now the projection in x direction, what we have here minus r, yeah, and here plus g sine alpha, okay? We have the angle alpha here. This is the force, or gravitational force, projected in x direction. In y direction here, g cosine alpha, and you have the friction here, yeah, force, it's r. Now we have minus r, g sine alpha, and this is equal to the mass multiplied by the acceleration in x direction. The same principle is used in y direction. Now there is no acceleration perpendicular to the path. Y is equal to 0. It's also the velocity is equal to 0. Then it means if we see there is the motion only in this direction, x, yeah, but there is no motion along y direction, okay? If you use, for example, coordinate system like this, x horizontal, y vertical, in this case, you have to project x along the motion direction and y also along the motion. Then you have always to try, for example, as for the polar coordinate system, if you have curvature or circular motion, it's better to use polar coordinate system than to use Cartesian coordinate system. Here, we can use, there is no circular motion, there is only horizontal motion along this direction. In this case, we can use the Cartesian coordinate system, but we must be clever to use the coordinate system because you are always free to do this. It's only to use the coordinate system along the direction of the motion. Yeah, this is will simplify, yeah, the equations and so on. Now, if we look here, there is the acceleration is equal to zero. Yeah, there is no motion along y direction. In this case, this terms here, it's equal to zero, like in static equation. Then we have the normal force. It's only G, the gravitational force, multiplied by cosine alpha. Now, if we come to here, R, it's only mu, the friction coefficient, multiplied by the normal force. Normal force is given by this equation. Yeah. Now we can replace here R by its value. Yeah. And then we get the acceleration here, G, the gravitational acceleration multiplied by, yeah, this, the sum of the two terms. Now what we do, we get the acceleration, okay, the equation for the acceleration in x direction, we integrate, yeah, twice or two times. Now we get the velocity and then we get the position, okay. For the integration to get the velocity, we get the constant C1. For the position, we get the constant, we get here the constant C2. To determine C1 and C2, always, yeah, we take the initial condition. Why? The initial condition, we know it, let's say, always. Then the initial condition, what we know, the acceleration was at rest, the particle or the mass m, what was at rest, then it means the velocity at time t equal to zero. It's zero. The position also is zero. Then we get C1 and C2 are equal to zero. Then we have here the equation of motion. Okay, acceleration, velocity, position. Okay. Now, time of the travel distance here, L, let's say, x equal to L, then we can get here the time from this equation, okay? From this equation where here we replace x by L, then we get the time, yeah, for the travel distance, okay? If we want to calculate the speed at the end of the motion, yeah, we get this equation, okay? We have the time t, we replace it by this one, yeah, this value. Then we get here x dot L. In the case of the frictionless case, that is means that mu is equal to zero, there is no friction. In this case, yeah, we get x dot, yeah, for the distance L is only 2 times GL sine alpha, means that in the frictionless case, we have this term here, which is equal to zero. It's the same speed as for the free fall with the length L sine alpha. Okay, I will stop now for today.